All right. Well, good afternoon. Good afternoon, everybody. Thank you. All right, thank you. So this will be, assuming I don't go over time, this will be the last lecture where we're doing kind of new material for the semester. And there's not a whole lot to do, really, so we've got to talk about the inclusion of time fixed effects in a panel data regression model. And we'll do that first. And then also the way in which standard errors are calculated for a panel data model with fixed effects. And again, there's not a whole lot new to say there, but there is one really important concept that lies behind the calculation of standard errors in panel models that we don't see in just cross-sectional time series models. And so that'll be the focus of the standard error conversation. And then we'll be done. All right, so this is just a quick refresher of the application that we're looking at to start with, so to introduce the concept of time fixed effects. So we've been looking at the relationship between the fatality rate due to motor accidents across the states of America and attempting to estimate what might be the causal effect of variations in beer taxes on that through a drink driving kind of a mechanism. So this Z prime gamma represents the time invariant omitted variables which may be hidden inside of this disturbance term. An example of this might be, something like the balance between urban and country driving in a particular state. Okay, so the kind of thing which varies clearly from state to state would have some kind of effect on the fatality rate, and at least within a short period of time. So we're looking at a panel data, the panel being collected over something like, what was it, 7 or 8 years or something? Not a huge period of time. Then that kind of variable plausibly doesn't change all that much during that time. So it doesn't have a T subscript on it. So we handle these kind of time invariant omitted variables by representing them, just all of them. So I've just mentioned one. We don't need to have a really clear and specific idea about what those omitted variables might be, just so long as whatever the time invariant factors are, they all get bundled into this single individual level intercept term alpha I, which is also called the fixed effects in this model. So each individual, or in this case each state, gets its own intercept in the regression. And we found that estimating the fixed effects regression on this data set here gave us a coefficient that was, I actually haven't put the pooled OLS here, but it gave us a coefficient that was kind of the complete opposite of what pooled OLS gave us. Okay? So pooled OLS says higher beer taxes are associated with higher fatality rates, but then when we allow for this state level heterogeneity, then that conclusion switches around and we get the negative effect, which I guess if you're a policymaker, that's what you might be looking for or hoping for or something. All right, so that's the story so far. Okay, so it's a negative coefficient. There's a standard error here, which we're going to come back to and just mention what's going on behind that standard error as well. But before we do that, let's just also mention the concept of time fixed effects, which is just kind of looking at the other dimension for possible variations and possible omitted variables. So in this case, we're looking at omitted variables which maybe vary over time but are constant across individuals. Or in this case, I guess we'd say constant across states. So we'll keep in the individual heterogeneity, so that's important. I think that's, so empirically we would say that's been demonstrated to be important because we put in the fixed effects and completely turned around the conclusions. So it seems like these fixed effects are doing something important here, okay? the individual fixed effects. All right, so we've now introduced this additional term here, the ST prime eta, which refers to heterogeneity across time. So things that are changing over time, but affecting all of the individuals kind of in the same way. There's not a subscript I on any of this stuff. So there's a couple of possible factors for this which are mentioned in the book. You know, one might be over a period of time there's an improvement in the safety features which are available on cars. And those cars would be available roughly equally across the states. And so what we might have here is an omitted variable in this regression which says, you know, safety features in cars are improving over time, having some effect on fatality rates. And if for some reason that was correlated with bee attacks, it doesn't need to be a causal link, just if there's a statistical relationship between safety features in cars and the level of bee attacks, then we would have an omitted variables problem arising from this as well. And remember, when we're looking at things that are changing over time, and especially if maybe they're trending. Now, we're not looking at a long period of time here, but just making a connection to our time series stuff. If safety improvements are going up, let's say, if we assign it in that direction, and if bee attacks also happen to be going up over this time, or even if they happen to be going down, I haven't checked, in either case, the simple fact that those variables trending in one direction or the other would induce some kind of statistical correlation between them. Okay? Might not be indication of a causal relationship of any sort, but it would give some kind of evidence of a statistical relationship, and that's enough to mess with the to mess with the omitted variables bias, to cause some omitted variables bias due to this omitted safety variable. All right, so we need to be, at least in principle, equally concerned about the possibility of these individual invariant omitted variables. And the logic is much the same, really. So once we've recognised that this is a possibility and that having the two dimensions in the panel data allows us to identify these kinds of effects, then just as we introduce a fixed effect for these individual level variables, we can introduce a fixed effect for these time-varying omitted variables as well. Okay? So from a logical perspective, it's just exactly the same deal, except that now the fixed effect has a subscript t instead of a subscript I. So it's like introducing now as well an additional intercept, if you like, or an additional constant term into this equation, which is different for each time period, but the same for each state. All right, so that's the kind of logic of it, I guess. It matches the individual one pretty much. To estimate, once you know how to estimate one of these things with individual fixed effects, then introducing the two is pretty easy. Just use almost exactly the same command. So here we're going to run a panel data linear model of the fatality rate on bee attacks on the same data set as before. We're still using the within transformation. So this within transformation, remember, is the idea that we take out sample averages. Now, in this case, when we're estimating this model, we have two directions of within transformation to carry out. Okay, so if we could first of all work out the time averages, as we did before, to remove these alpha i's, and then we'll also work out the individual level averages to remove the lambda t's. So take the mean over I, add up, divide by n, subtract that out, and you'll be rid of those lambda t's at that point. Okay, so this within transformation here is in fact operating on both of those effects because we're doing it two ways now. Okay, we're doing it on individuals and on the time dimension. So that's the one thing that we've changed here, is just to introduce both directions of fixed effects into this model. In this case, the coefficient now doesn't change it very much at all, really. So before it was minus 0.655 kind of thing. Now it's minus 0.64. So that's really not changing at all. So what that would suggest to you, at least from a robustness kind of perspective, is that whether we include the time fixed effects or not doesn't make a lot of difference. So whether or not you buy, for example, this safety story, or whether there's something else going on, like an overall macroeconomic story that might be possibly influencing these fatality rates, the empirical evidence is that allowing for those kinds of factors is just not making a lot of difference. So all it's doing is inflating the standard errors. And again, I'll mention in a minute. So conclusion number one, it would appear, so we could do formal tests. We don't quite have time to get involved in that. But from a practical perspective, are the time effects influencing our findings? Well, not really, not at all. So maybe they're just not needed. They do make the estimate less precise, okay? So by which I mean the standard error has gone up to 0.35. It used to be 0.28. And if 5% level of significance is your gold standard for stuff, then it has actually changed one conclusion. So this was significant at the 5% level before, and including the time fixed effects is just enough to tip that over the magic 5% level, if you take that literally. All right, so, whoops, let's go back. And I'll explain why that's affecting the standard errors in just a second. Notice these, we also have a dummy variable interpretation of this equation right here as well. So just as including the individual fixed effects, the alpha i's, was the same as including a full set of n dummy variables, one corresponding to each state, and that's what generates all those intercept terms, 48 intercept terms. We can also just include some dummy variables for the years as well. Okay, one dummy variable for each year, so 8 or 9 dummy variables, whatever the sample size is here. And then run OLS on that model, okay? So compared to using the within transformation, running OLS on that model is fantastically computationally clumsy. This is a small data set, so you can do it. It's no problem at all. You can just type LM into, in fact, there it is, just to prove it to you. There's LM typed into R with the state dummy variables and the year dummy variables, and even on a little laptop it executes like that. So that's no problem. But if you're dealing with seriously big panel data, then doing it this way is a bit of an issue. What you get, oh, and so this looks a bit funny right now, but if I just go and grab I think I've got it here. Yeah, there we go. So this is the program associated with this lecture, which is more or less the same as the last one as well. And the regression that we're talking about is this one right down the bottom. So if I'll just, oh, did you like that? Not really. Let me just make this screen a bit bigger. All right. This is what we've got for that last regression that we just ran. Okay, there's the coefficient on B attacks, minus 0.64, whatever it is. And then we have, so what I've printed out on the screen there is just the first state dummy variable, but there's actually 48 of those things. So this is the dummy variable corresponding to Alabama and Arizona and Arkansas and California. I'll give up guessing now, but anyway, they're all the states, right? One dummy variable for each of these states. And then down the end, we have dummy variables included for the years as well. And you can take a look at these significance levels. They do actually make sense here because we have, well, this is a panel data with a large N and a small t. So these time series intercept terms can be treated as being reasonably well estimated. We have 48 observations in a cross-sectional sense to estimate each one of these. So one of them seems to be significant, but the rest are not. And that's really what's behind the fact that it's just not making a lot of difference in this case, that including these time dummies or not. Okay, so in that overhead, what's going on, why there's that funny variable there, is that that's just the first of the 48 state dummies, and then there's the time dummies underneath. So just bear that in mind, that's not the full set of results. Now, what thinking about the regression as a dummy variable regression helps to make clear in your mind as to why including these dummies for time have increased the standard errors, even though it hasn't really changed the coefficient estimate nearly at all. So what we know, even from just second-year regression algebra or whatever, is that if you introduce a variable into a regression which is unnecessary, like its true coefficient is 0, you didn't need to include it, then the effect that that has on the coefficient estimates is not all that much. Including a variable whose true coefficient is 0 violates no assumptions. You still get your unbiasedness, you still get all the nice stuff, right? So including a variable that you didn't need to is not terrible. It's not like an omitted variable, which is kind of terrible, right? But what including an irrelevant variable does is that it does inflate standard errors. Okay? So putting in variables that you don't need to gives you bigger standard errors. And in this, that's just a fact of regression. It's not unique to panel data. Okay? So in this case, we have put in these time dummy variables, and the evidence is more or less that we didn't need to. I mean, you can quibble about one of the dummy variables, but on the whole, it seems like we didn't need to include these dummy variables. They didn't change the estimate that we care about hardly at all. But because we've included these variables that aren't really improving the fit of the model, the standard error has gone up. Okay? So on that basis, if you had these two sets of results sitting in front of you and say, well, which ones do I prefer to interpret? Probably lean towards interpreting the ones without the time effects. They don't seem to change anything important, but they are making the estimate less precise. So that's how you might think through that kind of comparison. Okay, so that's the time fixed effects kind of deal. Now you can run a panel model with time fixed effects and without individual fixed effects. That's much less commonly done, but there's nothing to stop you doing it if you think it's relevant. Okay, what we'll do now is just have a fairly brief and intuitive kind of discussion of statistical inference in panel data regression. So in a sense, this is revisiting our more theoretical unit where we went through the properties of the OLS and two-stage least squares estimators under some assumptions. So I think, well, we don't have the time and probably none of us have the energy to do all of that algebra again, but what I'll show you is that a lot of the flavour of the results carries over to these regressions in very much the same way. So if we understand what's going on in those OLS models, then with one important exception in the standard errors, we pretty much know everything that we need to know about panel data models as well, or at least these kinds of panel data models that we're looking at with large N and small t. All right, first of all, what do we need for the fixed effects estimator to be consistent for estimating beta 1? Okay, so that's particularly what we're after, is this kind of causal effect. What do we need? And so far as the standard errors are concerned, again, we'll just focus on estimating beta 1. Then we need to account for or allow for the fact, possibly, that we're estimating n of these intercept parameters, where n is our important sample size. Now, it turns out if we write the model in the correct way, that's actually not a big deal. But this is the point that we will just dwell on when we get there, which is that these disturbance terms here are very likely in practice to be autocorrelated across time. Okay? That is, it's more likely to be the case that they are autocorrelated than not. Okay? So if we get a simple random sample of individuals, we don't have correlation across individuals, but it is likely we'll have correlation across time, and our standard errors would better account for that. All right, so I'll have a bit of a chat about that when we get there. Yeah, and like I say, the answers that we'll provide here apply to this large n small t case, which is typically what's relevant to microeconometrics, for example. If you're doing more, macro international finance kind of stuff where your time dimension is also pretty large, then some of these answers can be different. So, the structure of the panel matters to these kinds of issues. All right, here's how we go about, well, first of all, writing down some assumptions that allow us to estimate the causal effect. Now, we did this kind of representation of the model into matrix form before. And you don't, strictly speaking, have to do this, but I think it makes things more transparent if you represent these things in matrix form. So, in particular, what we're doing is stacking up all of the observations over time. So this vector for y here consists of all of the observations for individual I, okay, or state I if you like, from time 1 up to time n. So it's a t by 1 vector. Now these individual fixed effects, they're like just intercept terms, constant terms. So they have an implicit kind of explanatory variable equal to 1. And then we have our explanatory variables here again for observation I, time 1 up to t. Okay, so we're stacking all of those up into these t-dimensional vectors. So we're going to consider this we're going to consider the regression one individual at a time, but with all of the time dimension taken into account in one hit, okay, in one vector. And there it is beautifully colour-coded. So the y vector now, instead of just a single y. Now this is the new bit here, this I subscript, well, that's an iota subscript t, is just the notation that we're referring to for a vector of ones. So that'll pop up a few times. The x and the v. So just remember, in this discussion now, these things that only have a single I subscript on them are vectors or matrices. All right, here are the sufficient conditions that are, here are some sufficient conditions for the consistency of the fixed effects regression estimator for beta 1 in particular. So, first of all, so they're sufficient, they're not necessary. You can push and pull these conditions in all kinds of directions, but these cover, this is the way that you will think about it in the usual kind of microeconometric setting. So, first of all, imagine that individuals are drawn in a simple random sample. So this is the same kind of concept that we've had whenever we've talked about sampling. We have a population in mind, we go to the population, we draw the sample in such a way that each individual in the population is equally likely to be included into the sample, and each individual is chosen independently of every other individual. Okay, those are the two important defining features of the simple random sample, and give us IID random variables, okay, across I. Right? But once we have chosen each of the individuals to be included into the sample in that way, we then follow those individuals over a certain period of time. Okay? So instead of just getting one measurement for each individual, we get a panel. We get a number of measurements for each individual. And that's kind of where this dependence over time comes in, because we're talking about the same individual being repeatedly measured. Okay? So because it's the same individual being measured repeatedly over time, there's kind of dependence in that direction, even though the individuals are independent across time. So when we talk about IID in this context, it is important to emphasise that that is across individuals only in this case. All right, so that's our sampling structure. So it's more or less the same as what we spoke about when we were doing theory for cross-sectional regressions. So the sampling structure is the same. And then here is our conditional expectations assumption. And we've had one of these before, and it's almost the same as before. It certainly looks that way. What it says is that the expected value of the VI, so remember the VI is this vector of disturbance terms here, conditional on the x's, and also conditional on these alpha i's. So these alpha i's, these individual effects, are themselves random, because if you draw another random sample of individuals, you get different alpha i's. Okay, anything with a subscript I on it is saying if you get a different individual, you get a different one of those. Okay, so different individuals give you different y's, x's, and alphas as well. So they're random variables, and we condition on those as well here. So if the expected value of the VI's, these disturbance terms, conditional on the x's and the alphas are equal to 0, then we will get consistency for beta 1 of the fixed effects regression estimator. Okay? So what we want to do is just to pause with this conditional expectations assumption right here and just have a quick talk about that. So it looks kind of familiar, right? So in a cross-sectional regression, we have one of these assumptions as well. If you want to consistently estimate a causal coefficient, then you need for the expected value of the disturbance term conditional on the x's to be equal to 0. Okay? So it's almost the same. We've got these alphas in there as well. The other thing that's different, though, is that it involves an assumption about a vector of disturbance terms, not just a single disturbance term. Okay? So when we say expected value of VI, we're talking about the whole vector. We're talking about T things now. So this is not really just one assumption, it's a vector of t assumptions that we're writing down. So if we write that out explicitly, that's how it appears, right? Just a reminder that the VI looks like this thing. And so this assumption that we're making here implies that the expected value of VI1 at time 1 is, let's say, unrelated to the x's at times 1 up to t and the alpha I, okay, for that individual, and all the way down to the end, so the disturbance at VI capital T, the last disturbance, has to be unrelated to the explanatory variables from time 1 up to t. And why that's just worth stopping and dwelling on for a minute is that we're no longer just asking that the disturbance term at time t be uncorrelated with the explanatory variable at time t. We're also requiring that the disturbance term be uncorrelated with the past and previous explanatory variables as well. Okay, so it brings in, this assumption is bringing in an assumption that the x's are not allowed to be correlated with the disturbances, even at lags, or at leads, if you like. Now, and we'll put that back into the B-attacks context in a minute to make some sense of what that might mean. But from an algebraic perspective, this assumption here is in fact T assumptions, okay? So what it's saying is, if we put words around what it's saying, then the V are the omitted causal factors. Remember, we're explicitly talking about trying to estimate a causal coefficient here. Okay? So if we want to estimate a causal coefficient, the VI is representing all the omitted causal factors, and it's important that they be unrelated to the included causal factors, the X's, and the individual heterogeneity, which is the alphas. So that's the assumption. If that's true, then, well, we won't do it, but the algebra to show that what you get is an unbiased and consistent estimator of beta looks very, 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 very like what we did for the cross-sectional regression a while ago. So it's kind of not new, but we'll omit that bit of proof. What it's worth, okay, so there's the conclusion. It's unbiased and consistent, as I said. What it's worth trying to do, though, is to tell this story of what this assumption means in this kind of context, just to try and wrap our heads around what it's saying and what it's not saying. Now, what might this VIT contain? So this contains the omitted factors, which maybe vary across states and across time, okay, in both directions. So anything that's either constant across, well, actually, I've left out the time fixed effect. So anything that's varying across states but is constant over time is already taken out by the individual fixed effects. And we could throw in a time fixed effect if we want to cope with those. So we're specifically interested in here stuff that varies in both dimensions. A few things that are mentioned in the textbook as being plausible candidates to be included in the VIs might be, for instance, the effects of a recession on road traffic. So this is an interesting correlation if you look at this stuff, which is if you have an economic downturn, then people drive less, if nothing else, because they're unemployed and don't have to go to work, but also they don't have, on average, as much money, and so they don't drive, or a car gets repossessed, all kinds of reasons. But it's very clear in the statistics that in a recession, the amount of car driving that happens goes down, and the amount of road accidents that happen go down, and hence road fatalities go down. Now, if it's also the case that during a recession, people, you could argue either way. Let's say that people buy less alcohol. They might try to numb the pain of a recession with more alcohol. But whichever way you go, maybe there's an arguable relationship between the state of the economy and the level of beer taxes. It's probably going the same way, let's say. So we could have a variable such as a recession, which clearly changes over time. Okay, so over a period of time, a recession hits, we have a couple of bad years, and then things start to pick up again. And it's plausibly correlated with the level of beer tax. Will have an effect on the fatality rate. And there's an explicit time dimension about this, which is worth thinking through as well. So it may be that when a recession first hits, it may not relate to the beer tax in that year, But if it relates to the B attacks in the following year, let's say, if it has a delayed effect, that's still a problem, okay? So even if the recession hits this year and doesn't affect B attacks receipts immediately, but has a lagged effect, that's still an issue. That would still be violating, you know, this kind of vector of conditions. So what we would be worried about there is, I guess, what this first line, for example, is saying. So VI1 is capturing, let's say, the effect of a recession in the first year of the sample. And that might be correlated with the B attacks receipts maybe the following year or the year after, which would be XI2 and XI3, okay? So if there's some kind of correlation there, then you have a problem, okay? So it's the kind of thing you don't immediately think about when you're trying to imagine conditions for validities of regressions or stuff. As, you know, is it possible that a disturbance today could affect my explanatory variable in a year or two time? Okay, but it is something to dwell on with these kinds of panel models, that it might be relevant. Okay. Now, the main thing is obviously not so much the details of the traffic accident literature, but just observe how this gets thought through, okay? The logic is basically the same as what we've seen with omitted variables before. You know, is the variable relevant for the outcome variable? Could the omitted variable be correlated with the included variable? Is there a plausible story to be told there? Okay, so this is the kind of logic that you take yourself through to think about is this omitted factor a threat to the consistent estimation of my causal effect? And I guess recessions hit different states differentially as well. So we would imagine that this could be a state variable effect. Other ones as well, changes in road quality over the time period. So different states have different levels of road construction going on over time, and so some of that might be funded with beer taxes. So you could make an argument that that's another plausible omitted variable. Variations in weather conditions would be ones that much less likely to have lagged effects. So if you have this is North America, if you have a bad winter there, then that's really not good for driving in. But then once the winter's gone, you don't really get so much of the lagged effects as you would in the case of, let's say, a recession. If the winter's really bad, maybe beer tax receipts go up as well. So you can try and make these connections between how these variables are related. All right, so I've given you that conversation. The variables themselves, okay, so I've just been talking about the relationships between the V and the fatality rate and the B attacks. Okay, those are the critical things to work out for whether the omitted variables story is important. In addition, we'll talk about standard errors now, and in addition, these variables that we're discussing, well, most of them anyway, are quite likely to have some correlation across time. Okay? So correlation with themselves, autocorrelation over time. Now, the B attacks, for instance, is likely to be autocorrelated. Now, this actually won't matter so much, but it's kind of easy to get your head around the idea of autocorrelation with a variable that's observed like this. So the B attacks variable itself is likely to have correlation. For example, a positive relationship between the B attacks in state I at time t and the B attacks in state I at time t minus 1. So it's in the same state, and we're just looking at the B attacks this year and next year. Okay? So what we would expect, on average, is that states this year with high B attacks are more likely to have higher B attacks next year as well. Okay? So these things don't just kind of chop and change around randomly. States tend to have fairly smooth kind of policy positions on taxing alcohol and stuff like that. So you would expect to see, in fact we probably look at the data I guess, but you would expect to see that there'd be some kind of positive autocorrelation in a variable such as that. Now this correlation here doesn't really enter into our standard error thoughts at all, but these other ones do. So the autocorrelation in the V's kind of matter. So for instance, if you get a VI which is corresponding to an omitted factor, so we've omitted, a road building program, then that's likely to have ongoing effects into the road fatality rate. Effects of recessions can linger for years, so we know that recessions, Recessions have varying lengths, but their effects typically are more than just a single year. So if the economy is below average this year, it's more likely to be below average next year, even if it's starting to recover. So there's some kind of autocorrelation there as well. So the point about that kind of logic is, again, not necessarily the specifics of that application, but just seeing the idea that because we have repeated observations on the same individuals or the same states, it is very likely that these VI disturbance terms will have correlation across time, because they're all disturbances referring to the same individual or state. Okay? So this is not something that we can just assume away and think, oh, it's not very likely. No, it's very likely in most of the kind of panel data situations that we're likely to see. Now, this autocorrelation here is different in its interpretation. I mean, statistically the same, but its interpretation is different from the time series models that we've been seeing quite recently. So when we were building time series models for the purposes of forecasting, then we were estimating a conditional expectation based on information up to time t-1. And an implication of trying to do that was that the disturbances or the prediction errors, the differences between the observations and the conditional expectations have to be mean zero, conditional mean of zero. In other words, they have to be not autocorrelated. Okay? So that was an implication of wanting to forecast is we'd better find ourselves a model which doesn't have any residual autocorrelation. And if we've got residual autocorrelation, we haven't got the right model yet. Okay? That was kind of a series of implications because we want to forecast. Well, we're not trying to forecast here. What we're trying to do here is measure a causal effect. And it's more or less an unavoidable implication of the structure of the data that we have that there will be some correlation over time. But that correlation over time does nothing to invalidate the consistency of the estimate of the causal effect that we want. Okay, so, I mean, I didn't lumber through all the proofs, but you could just go through all the proofs and you can see that the fixed effects regression estimator will be perfectly well unbiased and consistent regardless of the structure of the autocorrelation in the V's. Okay, whether the autocorrelation is there or not doesn't make any difference. But where it does make a difference, so it doesn't affect the consistency of our causal effect, so the autocorrelation doesn't matter there, but it does make a difference to the standard errors. And it can make quite a substantial difference to the standard errors. And this is important to allow for this, to kind of get things right in panel data regressions. All right, so we'll explain this in terms of a few formulae and just show how this appears in the calculation of standard errors for the panel data regression. So again, we take our original regression, and I've just included the individual effects here, but we could have time effects too. Okay, so having the time effects doesn't really change this dramatically. Even if we have time effects in here, time fixed effects, we could still expect to have some autocorrelation in these V's. Okay, so time effects are not some miracle way of getting rid of autocorrelation. It's probably still there. Might reduce it, but it'll probably be still there. All right, so this is our regression. We stack this up into a matrix form. So again, all of the observations for one individual across all of the time periods get stacked one on top of the other. This is a general representation now. I've allowed for a vector of x's here just so we have the full generality of formulae. So we could have multiple x's here, not just a single B-tax variable. So take this regression here, whack it with a within transformation so that the individual effects get knocked out, and having these tildes on the top of these variables denotes the fact that each of them has their time average removed. Okay, so just the standard within transformation at this point. And the question is this: how are we going to get standard errors for this thing? All right, so we've got ourselves this within transformed model, and you can see that the effect of that within transformation is to produce for us a regression model which looks for all the world like the kind of cross-sectional ones that we've seen earlier in the semester. Okay, it's got these funny tildes sitting on the top, but other than that, kind of algebraically, it's the same. It's the same structure. The only difference is we now have vectors of disturbances and vectors of y's and matrices of x's, okay? But in terms of how we deal with the calculation and derivations with this model. It is the same, just so long as we're careful with the matrix dimensions, right? So the fixed effect estimator looks like that. It is just an OLS estimator at the end of the day. Okay, you do the within transformation, then you do OLS. So that's a familiar formula right there, and that OLS formula gives us some residuals, just like before. The residuals are a vector of residuals now, so remember this funny thing here is a t by 1 vector of residuals for individual I stacked up time 1 up to t. All right, if we go back, way back to week, I forget, I did mean to look it up, week 4 or 5 or something, when we dealt with the theory of the OLS estimator, we figured out that the form for the heteroscedasticity consistent variance matrix looks like this. Okay, and I've copied it out with identical notation. The only difference is in this omega xv. So the omega xx is the same. Well, it's got tildes on the x's because they've been within transformed, but otherwise it's the same. In this omega xv, it's almost the same, but what we had back in the day was vi squared times x transpose. Well, vi is now a vector, so we can't square it, and instead it has a v times a v transpose. All right, so those expressions are essentially the same. Apart from that one difference right there, they're essentially the same as what we've seen before. And because of that, they will automatically be consistent if there is heteroscedasticity. So if the variance of these v's is in some way related to the x's, using this form of variance matrix will sort that out. Okay? So this is by far the most common way that these things get calculated. So we're allowing for heteroscedasticity in the usual way. Heteroscedasticity, roughly speaking, is the correlation or the covariance between the squared residuals and the x's. Okay? So here are the squared residuals, v times v transpose, because they're vectors, that's now the square. And then we're taking covariances with these x's here. Okay? That's the intuition of why that works, is we're taking into account the fact that there is possibly some covariance there. We're not assuming it away. So I just spent a while telling you about how important all that autocorrelation stuff is. Where does that come into it? Well, it's automatically taken into account in that formula as well. So take a look at this omega hat xv with this form of the v's thrown in here like this. What this is allowing for, if we just expand out what this vector looks like and what this vector looks like, they look like that. Okay? And what you get when you multiply this vector times this vector is you get this big t by t matrix. You'll get a v1 times a v1, and you'll get a v1 times a vt. Okay? And when you've got the v1 times the vt, what that's doing is it's estimating what is the possible correlation between v1 and vt, or the autocorrelation between v1 and vt. And all of the others in between, there's a v2 there, so the correlation between v1 and v2 is being estimated in this form of variance matrix. So the point is, if we set things up in this kind of vector structure and then apply our covariance matrix logic that we've seen before, then automatically for free without doing any work, we're getting heteroscedasticity consistency and we're getting autocorrelation consistency as well. Okay? Yeah, should have that up. Now, there's language for this in the panel data field, which is called clustering the standard errors, or clustering the variances. And so what that refers to, what that word refers to, is the fact that in this case we're clustering on the individuals, meaning for each individual we cluster together all of the observations into one cluster or one vector. So this VI, for example, is the residuals, or the cluster if you want, of all of the residuals for individual I. Okay? So that's a cluster for individual I, then a cluster for all the other individuals. And the standard errors, the standard error formula is calculated in terms of those clusters. So the VIs are treated all together, all in one hit. And in the process of doing so, we automatically produce all of these cross products that takes into account the autocorrelation. So doing it that way doesn't seem all that important at all. It's like, what's the big deal? Well, if you just estimate regressions without using specific panel data routines, such as the PLM kind of thing, so if you just use an LM with some dummy variables, for example, then it will automatically use what we would call an unclustered formula, which would, instead of stacking up this regression into its vectors and treating the time dimension all together, you would work with this original regression, disaggregate it into its i's and its t's, and work out the variance, assuming implicitly or otherwise that there was no correlation between across the I or the t dimension. And if you did that, you would get a formula like this. And that, in some ways, looks a bit like what we've seen before. This is still heteroscedasticity consistent because we have the squared residuals being related to the x's. Okay, so we haven't gone all the way and just done OLS standard errors here. But there's no cross products here. So the VIT is not being allowed to correlate with the VIS for any t not equal to s. All right, so that's, I guess, the simplest form of clustering that you can do, where you take all of the observations for each individual, consider them together in a vector or a cluster, and construct the standard error formula from those clusters constructed for individuals. Now, different clusters can be done. You could cluster on time if that was relevant for some reason, or you can cluster on other variables as well. So there's quite a lot of variations on this kind of clustering that can be done according to where you think the dependence might occur between the observations. But this clustering on individuals certainly is the most common starting point, at least. And just to show you that, well, how it's done and the difference that it can make. So these regressions that we've been estimating up until this point have all included this option, and that will automatically be generating the nice clustered standard errors on individuals anyway. So we had those for free, and we had those kinds of results. Now, if you instead did the regression this way, so that's using the panel data approach, okay, with the within transformation and just the individual fixed effects. So if we did the same thing here, so this is just doing OLS at this point, and we're including the B attacks and the state dummy variables, so that's the fixed effects right there, the individual level fixed effects. And doing the HC standard errors, you'll notice it's different, okay? It's not hugely different in this case, but it's different enough, right? So this estimation here would be unclustered because the standard OLS command has no notion of this panel data structure. It doesn't know that there's individuals and individual dimensions and time dimensions. It just says, oh, this is a bunch of observations, so let's go regress them. Okay, so it doesn't take that into account. And in this case, it's come up with a standard error of 0.23 as opposed to this one, which is a standard error of 0.29, let's say. That's kind of a 25% difference, roughly speaking. So 25% difference in standard errors, you know, translates into confidence intervals, stuff like that. It can matter. So if we believe that there is, well, if we have a suspicion even that there may be some autocorrelation across time, then this clustered standard error is the way to do it. And if you're doing this panel data stuff, you know, kind of for real, for actual research or something, you would pretty much 99.9% of the time use some form of clustering because there's always going to be some form of dependence across these individual level observations in this kind of context. So these standard errors here, if you compared those two results, you would likely say, well, I don't really trust these unclustered standard errors. They're different, and they're probably different because they're not allowing for the autocorrelation. So that's how you would think through the differences that you got there if you happen to estimate them these two different ways.